Hello everybody, I'm making this video to demonstrate the AVX, which stands for Advanced Vector Extension of Modern Computers. AVX is basically an instruction set in the computer that performs multiple floating point operations at the same time. So if you have multiple floating point operations, the same instructions but operated on different data, you want to do the same instructions at the same time, AVX can do them together more efficiently than if you do one instruction at a time. So let's demonstrate this with a very simple C code over here. Okay, we are going to make a test.c, and as every C file, we are going to make a main program. So the first thing we want to do is to make a vector or array of floating points. So here, let's say we make an array of A with n numbers, where let's do a constant n is equal to 8, just for example. So 8 floating points. I'm pretty sure that the size of AVX, I think the newest extension supports a 512-bit operation. Each floating point is 64 bits if it's double precision and 32 bits if it's single precision. So if the vector operation is 512-bit wide, that means it can support 16 floating point operations at the same time, which means if we perform an operation with 8 array at a time, it should be roughly the same speed as if you are performing the same operation with 16 floating point at the same time. So let's see how it works. So let's first of all perform a loop, and I'll call the loop a time loop because we are repeating the same instruction for many times, and each time we are going to be doing the instruction on an array of 8 members. So let's just make something really big here. Maybe this is too big. Let's do 20 million. Okay, we are going to loop through this loop for 20 million times, and for int I goes from 0 to n, we are going to do some non-trivial operation to this array A. Okay, so first of all, I think it's a good idea to initialize A to something non-trivial. Let's just say A of I is equal to I, right? Just to make them something different so that the compiler wouldn't perform an optimization that, okay, all these floating points are actually the same value, so it'll just do it once. I don't know if compilers are that smart yet, but maybe they are. So let's make them different in the beginning. And we need to do some non-trivial operations. So maybe let's make it just something random, divided by 1 plus AI times AI times AI. Okay, so this I think is going to be a simple operation that involves multiplication, division, addition, and I think it'll prevent A from going into infinity. Let's see. Okay, and at the end, let's do something to every member of AI so that the compiler wouldn't optimize all of this hard work away. I mean, let's assume the compilers is really lazy. So let's make a floating point sum of A, and let's loop over the array again, and let's say sum of A plus equal to AI, and this should be 0.0f. All right, and let's just print it out. Printf and sum of A. Okay, so because we have Oh, okay. So because we have this printf statement, we have to include standard io.h, and we also want to time our operations. So we are going to include time.h. So we are going to say, okay, time t0 is equal to clock. So that tells me what is the time before these operations. And I'm also going to say t1 is equal to clock over here. That is going to give me the time after these operations. Okay. After this, I also want to print out what n is. And I'm going to print out the number of floating points operations per second, which is n times, okay, so this number is so large, I'm afraid I don't know for sure if it is going to overflow our integer, so let's make it float. So all the calculations are floats. We won't have an overflow. Let's just do it like this. Float flops is equal to how many operations it has done. Okay, and each one of them has, let's say, one multiplication, one addition, 1, 2. Okay, let's just count the operations. 1, 2, 3, 4, 5, 6. Okay, I'll multiply by 6. And I need to divide by the total time. Float time is going to be t1 minus t0 divided by float of clocks per sec. Yeah, okay, that's the right constant. Okay, so it has elapsed for that much time, and so the floating point operations per second should be divided by time. Okay, flops. So let's see for a width of n how sum a, n, and flops. Okay, and I'm going to run a, and the flops is equal to this. That's kind of a too much larger number. I'm going to use a gigaflops. So I'm going to divide by 10 to the 9th. Oops. G flops. Okay, so this code is running at 4.6 gigaflops per second. All right. So this is with a width of 8. So let's package that into a function with the argument const int n, so that we can call this function. Let's call this test. Actually, we don't need any return value, so we'll get rid of this. So let's test with 8, which I think is going to give us the same, now this time 4 point something gigaflops per second. Let's also do that with 4, 8, 16, 22, 64, 128. And let's see how that works. That's cool. So it looks like the code scales up all the way to 64 floating point operations at the same time. So with an array of 64 floating points, it achieves the maximum floating point operations per second, which is about 20 billion floating point operations per second. That's pretty much how powerful this laptop is. So I'm having a Microsoft Surface Pro 4 and with the Intel Core i7 CPU. And actually, just to be a little bit interesting. I think I've learned there is this flag, compiler flag. If I Google search I can specifically tune the code to corei7 AVX. Okay, so what I need to do is to set dash march equal to corei7 AVX. So let's run this again to see how well that performs. It's a bit disappointing. Okay. So with this specific flag, it doesn't look like I'm gaining a lot of flops. But maybe wait a second. Let's test this to 226 to see how that works. Wow. So with 226, I'm getting even more floating point operations per second. What if I don't include this corei7 AVX? It looks like the corei7 AVX actually does something. What if I include 512? All right. Yeah, this is consistent. Wow, with I'm getting 26.2 gigaflops per second.